This is module number 2 from my online Tensor Introduction for Non-Mathematicians course. Here we discuss the primal vector as well as the primal space. As the course title suggests, these videos are aimed at scientists and engineers with some background in linear algebra who want to learn more about tensors as applied to something like machine learning. This module introduces the primal vector type tensor as a representation of physical-like values in some n-dimensional space. Specifically, we're going to discuss how this tensor is composed of a primal basis set as well as array of coefficients, how it differs or how the primal vector as a tensor differs from a traditional array, how a primal vector may represent a position within a normal 3D space as an example. We'll discuss the primal space as a representation of all the vectors relevant to our problem or application, as well as we'll discuss how it defines the ways in which primal vectors may be added, scaled, and manipulated. I have written a text to accompany these lectures. A link to that text will be provided in the description below once it's publicly available. I apologize, I'm still working on that. If you have questions or corrections, please place them in the comment section below. I'll try to address them as quickly as possible. And as always, please like and subscribe if you'd like to see more videos like this. So let's dive into the section about linear algebraic structures. Hopefully, most viewers at this point are familiar with what an array or a matrix is. We used those terms in the previous section. Both are data structures that store and organize elements of similar size. Arrays are represented with, in our work, and this is about notation really, arrays in our work are represented with a lowercase, non-italic, bold font. Matrices are represented with an uppercase, non-italic, bold font, and then a single element of either uses the same symbol but with a non-bold italic font. And we're gonna show an example of that in 1 second. All indices are separated by brackets. So superscripts represent row indices. And those are called contravariant indices. We'll talk more about that in a second. Subscripts represent column indices, and we're going to later call those covariant indices. Some texts, and this goes back to some of the confusion about what a tensor is, use the terms vector and array interchangeably. However, when we're talking about tensors, those two have very different meanings. All right. So here we have an example of a row-oriented array. You can see that it has a bold, non-italic symbol, and then the individual elements are non-bold, italic. They have the same subscript, but they have this additional index, which is bracketed. And because we're talking about different columns, they are subscripts. So we have, trying to draw it as bold, X row, and that is equal to, and I'll try to draw it as italic, X row 1, X row 2, ... all the way till the end. Now here we have a matrix expression where we have Y column is equal to X column times a matrix A. Now the green and the teal circles I think may be masking what it is that we want to show, but I can write it on the next slide. So we have a matrix which I call A, okay, and that's my attempt to put it in bold, and it's multiplied by a column array which I'm calling X column. I'm just going to say C, and we can expand that as shown here. So this is a 2 by 2 matrix. As such, it has 4 elements. So we have, this is italic, A, and so let me write that 4 times. We have 4 A's, all right. Now, for the first column, right, we have 1 and 1. For the second column, we have 2 and 2. So we are using the subscript indices to indicate the column, and then the superscript. So for the first row, we have 1 and 1, and then we have 2 and 2, and then we multiply that by, this is again supposed to be italic, xc1 and xc2. So we use the brackets to separate indices from other types of identifiers, such as the xc. So that's what I was trying to show right here, although I think my highlights may have masked it more than I wanted to. And then here you can actually see the product of those two together, and this obeys the general matrix math that you're used to seeing. And over here we have a column-oriented array, and so we can see subscripts denote column indices, which column along a single row, and the superscript index denotes row indices, which column, this should be changed, which row along a single column. Sorry for that mistake. I'll fix that. So that's really more about the notation that we're using. And I think you'll get used to that as we move forward into more examples. All right. So that was really just a very brief mini section. I'm not going to make a separate video on the notation, obviously. Let's move into the real meat of this lecture, and that has to do with the primal vector as a type of tensor. Now, this may be terminology that you're not familiar with, that you haven't heard before, and that's fine. Let's introduce it here. So what is a primal vector? A primal vector is the most fundamental tensor type. We generally use it to represent a value within some n-dimensional space. So if you remember from the ball example, right, we used what we'll find out was a primal vector to describe the velocity at a certain point in time. It does resemble an array in many ways. The main way it does so is the fact that it only has values along a single column. Now, both an array and a primal vector represent quantities that cannot be expressed by a single number. However, unlike the array, a vector is inherently composed of two things. And hopefully that should be familiar. We've already shown what those two things are. We have a primal basis vector set, which we generally represent with some variation of the variable b. Okay, it defines the axes to which a given value is being projected, or the referential directions and unit lengths associated with it. We then have the coefficients, or the coordinate array, and they define exactly how a value is projected to the axes defined up above. And it represents the coefficients that you can apply to that set that generate the desired resultant tensor v, as shown on the next slide. Now, although a vector as a type of tensor is invariant to change of basis, the components that make it, from which it's generated, are not. And so here we have an example, right? We have vector v, hence why it has the arrow hat, and this is equal to some basis set b times the coefficients v, what we're calling v column. Now, we must represent the coefficient array as a single column, and we represent the basis set as a single row. Although we can think of it as a matrix because it's a single row that each sub-element is, depending on how you look at it, can be thought of as two columns of values. I don't want to get too caught up in that because we'll see why that makes sense later. Let's try to keep it simple at this point. And so over here, we have the product of the two, and again, we see that the resultant vector is equal to the first coefficient times the first basis vector, second coefficient times second basis vector, and then obviously you could continue that on if you had a higher number of dimensions. So the primal basis set defines the axes to which a given value is projected, or the referential directions and unit lengths associated with it. The coefficient or coordinate array, and I know there's some repetition here, represents the coefficients applied to that set B and generate the desired resultant tensor. So this right here is what we call our primal vector, and that's one type of tensor. So that was a 2D example. On the previous slide, we can present a 3D example. And so down here, you see we have a different vector. It's the product of some basis set we call B3D. And that contains 3 different basis vectors, which we call B3D1, B3D2, B3D3. And we multiply that by our coefficients, or our coordinate array V. And you can see over here, there's a visualization of how you can generate a vector from the linear combination of those 3 bases. So here we have our first basis, our second basis, our third basis. If we look at the gray arrow right here, we'll see that it may be generated by a linear combination of those 3 bases, right? If we go up 2.5 units and we go to the right 3.5 units, and then we go inward or outside, project from the screen by 2 units, we get this resultant vector right here. And so we apply that. We have 2.5 times our first basis, 3.5 times our second basis, and 2.0 times our third basis. And we get our resultant tensor. I think this is the type of vector addition that most of you are familiar with from work in trigonometry or geometry. So a primal space associated with a vector typically refers to that in which the vector resides. It consists of all the possible linear combinations of the basis vectors, with the basis vectors, right, being represented by the axes. It also defines certain fundamental characteristics of vectors, their components, and their interactions with one another. One fundamental characteristic is the space's dimensionality, which is the number of orthogonal or linearly independent directions that exist within that space. The space that we live in, our universe, if you don't count time, is 3 dimensions, right? I can move forward and backward without changing my position right, left, up, down. I can move right, left without changing my position in the other 2 orthogonal directions, vice versa. And if you look at a piece of paper, right, you really only have 2 orthogonal directions, up and down versus right and left. In more formal terms, a primal space is composed of vectors and scalars that may sum and scale in some predictable manner. So now we're going to get into a more mathematically accurate description of our primal space. It's composed of a set of vectors, which is described by this script here. A vector set to which math operations may be applied. We also have a set of scalar values. Now in this PowerPoint, we're going to use the script R to represent real numbers / scalar numbers. So we're just going to assume all scalars are real, and obviously all real values are scalar. So for a given vector space, an array or set of scalar numbers is defined and used to scale those vectors. This is essentially our coordinate array. Now, we can scale it using other numbers, right? For certain types of basis transformations, we can also use scalars. So this bullet right here is not limited to just the product of the basis set and the coefficients. We also have a vector addition rule and a vector scaling rule, which tells us how the vectors may be added. I think most of you are familiar with how that works. Essentially, the vectors are added, head to tail, and then you get the resultant vector. And then the scaling, essentially, and we'll show that on the next slide, but you can essentially take any vector and simply multiply a coefficient by it, and that extends its length by that value. So here are some scaling and addition rules associated with a vector. I haven't included them all. For example, VA plus 0 equals VA. I mean, these are what I would consider to be the most fundamental but non-trivial rules. And in general, vectors obey the superposition principle. So what we can see is with respect to scaling, right, you would distribute, if we're applying a coefficient alpha to two vectors, or the sum of two vectors, that would get distributed to both the vectors. We see commutivity for addition, which means we can reverse the order here, as well as associativity for addition, meaning that if we're adding three vectors together, it really doesn't matter whether we calculate the sum of the first two and then the last, or the last two and then the first. We can do that any way we want. But largely, the vectors, they obey the same rules as any linear operator would. Hopefully you got a lot out of this video, this module on primal vectors and primal spaces. The next module will define some fundamental characteristics of algebraic objects, a bit of background that's going to be required for us to understand later modules. A link to the next lecture is available in the description below, or it will be available when it's posted very soon. And I look forward to reading your questions and potentially corrections in the comment section.